Right now, you're floating inside an enormous cosmic hole, and almost no one is talking about it. Forget the comforting image of a universe filled uniformly with galaxies drifting serenely apart. If you pull back far enough, the cosmos reveals itself as a vast, luminous web, dense filaments of galaxies and clusters woven together like threads of light, separated by immense, shadowy voids that swallow most of space. These underdense regions dominate the volume of the observable universe, often accounting for the majority of its emptiness. But here's the unsettling part. Our own Milky Way, our entire local group, and a significant chunk of our cosmic neighborhood may lie deep within one of the largest such holes ever proposed, the KBC void, or local hole. Estimates place it at roughly 600 megaparsecs across, about 2 billion light-years in diameter, with matter density noticeably lower than the cosmic average. We are not on a bustling galactic highway. We are drifting in the cosmic suburbs, perhaps even near its center, and this position might be quietly reshaping everything we think we know about the universe. At first glance, living in a void sounds like harmless trivia, a slightly emptier patch of space. So what? But this isn't just about sparse star fields or fewer neighbors. Our vantage point inside this underdensity could be systematically distorting our most fundamental measurements of reality itself. For years, cosmologists have wrestled with one of the most stubborn puzzles in modern science: the Hubble tension. Two independent ways of measuring how fast the universe is expanding give stubbornly different answers. One probes the ancient universe through the cosmic microwave background, the faint glow from 380,000 years after the Big Bang. Using the standard lambda CDM model, this yields an expansion rate, or Hubble constant, around 67 kilometers per second per megaparsec. The other method looks at our local cosmic backyard, using pulsating C-feed variables to calibrate distances to Type 1a supernovae, those reliable standard candles. It stubbornly returns about 73.5 kilometers per second per megaparsec, a roughly 9 to 10% discrepancy that is only sharpened with recent data. This isn't a minor rounding error. In cosmology, such a gap is seismic. The expansion rate underpins calculations of the universe's age, its composition, and its ultimate fate. A higher local value implies a younger cosmos, clashing with the ages of the oldest stars and galaxies we observe. Yet, both methods have been refined relentlessly by missions like Planck, Hubble, and now JWST. Systematic errors have been hunted down. The probability that this is mere noise hovers near vanishing. Something fundamental is off. The standard model explains so much else with stunning precision, yet here it hits a wall. And one provocative idea suggests the problem isn't the rulers or new physics in the early universe. The problem might be exactly where we are standing. Imagine the universe as a giant, transparent bubble. Its walls are thick with galaxy clusters, filaments heavy with dark matter and ordinary matter. The interior is far emptier. Place the Milky Way somewhere inside, not necessarily dead center, but well within this depression. Gravity doesn't care about emptiness. It responds to mass. With almost nothing pulling from within the void, the massive structures on the distant edges exert an overwhelming tug. Galaxies inside don't just sit still. They begin a slow, collective drift outward toward those denser walls. This creates a local outflow, a subtle but measurable flow superimposed on the universe's overall expansion. When our telescopes track nearby galaxies receding, part of what we measure as cosmic expansion might actually be this gravitational slide out of the hole. That extra velocity could inflate our local Hubble constant, bridging the gap with the distant ruler without breaking the broader model. The evidence for this local hole isn't speculation pulled from thin air. It emerged from painstaking galaxy counts across wavelengths, from optical and infrared surveys to X-ray and radio data. Researchers like Keenan, Barger, and Cowie identified a significant underdensity extending out to hundreds of millions of light-years. More recent analyses, incorporating wide sky coverage, suggest the region may be about 20 to 46% less dense than average, depending on the exact metrics and corrections for redshift space distortions. The Milky Way sits within a few hundred million light-years of its approximate center, embedded in the Laniakea supercluster, which itself appears partially nestled inside this larger underdensity. Simulations like the Millennium XXL struggle to produce voids this vast and deep within standard lambda CDM, placing the KBC structure in tension with expectations, sometimes quantified at high significance levels. Yet, observations across multiple tracers keep pointing in the same direction. This isn't empty space in the absolute sense. The void still contains galaxies, including our own, and structures like the local group. But relative to the cosmic mean, matter is sparse. Voids form naturally in the cosmic web through gravitational instability. Tiny density fluctuations in the early universe, seeded by inflation and amplified over cosmic time, grow into filaments where matter collapses and voids where it evacuates. Inside these underdense regions, gravity's grip is weaker because there are fewer masses nearby to pull on one another. Dark energy, driving accelerated expansion, faces less resistance here. As a result, voids expand faster than average regions, becoming ever emptier over time. This is a standard prediction, but a void as large as the proposed KBC challenges the upper limits of what lambda CDM comfortably allows on these scales. Now, consider the implications for our motion. Relative to the cosmic microwave background, the closest thing we have to a universal rest frame, our local group hurtles at about 600 kilometers per second toward the Great Attractor and the even larger Shapley supercluster. In the void hypothesis, this bulk flow gains a natural explanation. We're riding the outward current, pulled by the surrounding walls. It's not random peculiar velocity, but a coherent response to the density gradient. Telescopes capture real motion, but interpreting it purely as Hubble flow adds an artificial boost to the local expansion rate. Models incorporating this outflow can reconcile the local and distant measurements without invoking exotic early universe physics or major revisions to dark energy. Recent work exploring redshift dependence shows that such effects would primarily influence very low redshift observations, aligning with where the tension most prominently appears. Yet the hypothesis remains precisely that, a hypothesis under active investigation. Not every dataset agrees on the void's depth or exact boundaries. Some analyses find milder underdensities, and standard simulations, while strained, aren't entirely ruled out when cosmic variance and selection effects are pushed to their limits. Ongoing surveys with instruments like Euclid, the Vera C. Rubin Observatory, and DESI are mapping larger volumes with unprecedented precision, probing galaxy distributions, peculiar velocities, and baryon acoustic oscillations at intermediate redshifts. Kinematic Sunyaev-Zeldovich effects, fast radio bursts, and future redshift drift measurements could provide independent tests of coherent outflows. If the void holds up, it would represent a triumph of observational cosmology revealing a structural feature that subtly warps our perspective. Think about what this means for our cosmic address. We belong to the local group, 24 galaxies bound by gravity, dominated by the Milky Way and Andromeda. This group sits within the Virgo supercluster, which in turn is part of the Laniakea supercluster spanning over 500 million light-years. But if Laniakea is itself influenced by the larger KBC underdensity, our local environment is quieter than average. Fewer galaxy mergers, less intense tidal interactions, reduced exposure to the ferocious radiation from distant, active galactic nuclei. In denser cosmic metropolises, frequent collisions trigger starbursts, feed supermassive black holes, and scatter heavy elements. Here, stability reigns longer. Life's emergence on Earth relied on countless local factors: our Sun's stability, Jupiter's protective gravity, plate tectonics, the Moon's tides. A calmer neighborhood might not be the direct cause of life, but it could tilt the odds toward long-term habitability by lowering the cadence of existential threats from space. This is cautious territory, grounded in the recognition that cosmic conditions vary, and our sample of one inhabited world sits where it does. The dynamics inside a void also touch the universe's grand evolution. Gravity slows local expansion in overdense regions by pulling matter together. In voids, with lower density, that breaking is feebler. Dark energy thus dominates more readily, hollowing them out further. Over billions of years, this accentuates the contrast in the cosmic web. Our position grants a clearer, less obstructed view in some directions, but it also means the light we receive from distant objects has traveled through a slightly different gravitational landscape. Gravitational redshift and lensing effects could carry subtle imprints. Some analyses even explore whether the integrated Sachs-Wolf effect, or CMB foregrounds, show hints of stronger signals consistent with the local underdensity. Zoom out even further, and the void becomes a rehearsal for the universe's lonely future. The expansion is accelerating. In tens of billions of years, galaxies beyond our local supercluster will recede faster than light can bridge the gap, vanishing beyond the cosmic event horizon. The cosmic microwave background will stretch and cool into oblivion. Future astronomers, perhaps an emerged Milky Way Andromeda galaxy, might gaze into a sky that appears static and isolated, with no visible expansion or relic radiation to hint at a hotter, denser past. Their calculations would be flawless yet incomplete, leading them to conclude their single galaxy is the entirety of existence. Just as our local whole might be gently misleading us today about the true global expansion rate. The cosmos is a master of perspective. What we measure is real, but filtered through our specific location in the web. This realization carries a profound humility. We build ever more powerful telescopes, JWST, peering into the first galaxies, future missions like the Nancy Grace Roman Space Telescope mapping dark energy with exquisite detail, concepts for gravitational wave observatories in space. We chase precision to the percent level and beyond, yet the universe never reveals itself fully from any single point. It shows what can be glimpsed from here, now, in this particular underdense pocket. The KBC void, if confirmed, wouldn't invalidate cosmology. It would refine it, reminding us that large-scale structure matters on GPC scales in ways we are only beginning to fully appreciate. It bridges observations that once seemed irreconcilable and opens doors to testing modified gravity or refined models of structure formation. Our tools improve daily. DESI's baryon acoustic oscillation data, supernova surveys, weak lensing maps, all converging on tighter constraints. If the void solution strengthens, it could resolve the Hubble tension as a late universe, local phenomenon, preserving the successes of the early universe predictions. Distinguishing it from background-level modifications to the Friedmann equations remains a key challenge, demanding better mapping of the local velocity field and density contrasts. The coming decades promise clarity. Ultimately, living in a cosmic whole isn't a flaw in our understanding. It's an invitation to look deeper. The emptiness around us isn't mere absence. It's a sculptor of motion, a shaper of perspective, a quiet player in the drama of expansion. It whispers that our measurements are contextual, our view privileged yet limited. In that vast web of filaments and voids, we occupy one small node, drifting slowly toward denser shores on timescales that dwarf human existence. The journey reveals not just the architecture of the universe, but the nature of knowledge itself, always partial, always from somewhere specific. How many other illusions does the cosmos hold? How many more traps await in its uncharted structures? The story of the local whole is far from over. It is, in the end, a story about discovery, about the courage to question our assumptions, and about finding wonder in the very space that surrounds us. A void, it turns out, is never just empty. Sometimes, a void is the key that unlocks the larger truth. Thanks for watching. If this journey through our surprising cosmic neighborhood sparked questions or awe, dive deeper in the comments. What do you think this means for our place in the universe? Share with fellow explorers, and subscribe for more stories that reveal the hidden layers of reality. The cosmos is calling.